pleasure, and also on behalf of the whole organizing committee, to introduce our last speaker for this conference and this really beautiful event, Stefano Trillo, talking about the nonlinear stage of modulation instability. And Stefano, the stage is yours.
Okay, Matteo, thanks a lot, and thanks to the organizer for the invitation. So actually, first of all, I would like to acknowledge the collaboration. So main one is with Lille, a group of Musso and Matteo Conforti. We did a lot together. And then you can see the names. I mean, they are very well known in the community. Nail, Gino, Amin, Miguel, and also the group by Kasparian in Geneva. And okay, so here is the outline, essentially talking about focusing NLS and the nonlinear modulation instability. So essentially, we look at the problem as a symmetry breaking phenomenon, and essentially, I'm talking about the nonlinear Schrodinger equation homoclinic structure, DMI, and if you wish, the underlying Fermi-Pascaud recurrence. And okay, so I hope I will not annoy the audience to death, because I'm going to speak about mainly experiments and concepts. So this is the second point, but I will mention tools, and we privilege predictive theoretical tools, and I will give 3 examples. So what we call extraordinary modulation instability, which is actually surprising in the stability region. The effect of damping in the nonlinear modulation instability, what we call breather freezing. I will tell about that, and if I have time, talking a bit about localized perturbation in the nonlinear MI. Okay, so let's start with very simple stuff. Okay, so you have to be careful about the notation, because I use optics notation. So essentially, evolution is in Z, and the transverse variable is time. And everybody knows in this audience, if I take psi naught initial value as 1, which is a background of pump, plus 2 sidebands, and these sidebands are very small, I do the linear stability analysis, and I get this picture. So the gain, which is the eigenvalue of the linear stability analysis, is different from 0 between frequency that range from 0 to 2. But actually, 30 years ago, we made an approach to show that we can do better than that. You can continue the modulation instability into the nonlinear regime. This was with Babnitz. And so essentially, you take an ansatz like the psi is the pump plus symmetric sidebands. Then you inject in the nonlinear Schrodinger equation. You neglect all the other harmonics of the sidebands, and you end up with a very simple ODEs. And these ODEs are actually Hamiltonian. This is not surprising, because it's the nonlinear Schrodinger is Hamiltonian itself. And I want to emphasize that the conjugate variable are eta1, which is a fraction of the sidebands. And this is, of course, when eta1 is growing, the pump is decreasing. So they are connected. And there is a conjugate variable, which is a difference in angle, in phase, between the sidebands and the pump. And I tell this because throughout the talk, I will use these variables because they are very relevant. And so what you can do is actually, something is not working here. Okay, so essentially what you do is a bifurcation analysis of this Hamiltonian. And you can realize that actually this modulation instability is associated with a pitchfork bifurcation of the background, exactly at the cutoff frequency 2. And the 2 stable branches actually represent dinoidal waves of the nonlinear Schrodinger equation, and the background becomes unstable inside the region. So this is not surprising. And you associate a phase space, the phase plane actually, to this behavior. And so essentially this phase plane that we are using, which are Cartesian coordinates associated with theta 1 and delta phi, tells that actually the modulation instability is a symmetry breaking phenomenon, because you go from orbits which are very trivial, like this one, to a broken symmetry where you have a separatrix, which is nothing but the accommodative breather, and this separatrix separates orbits which are outside or inside a standard figure of 8 picture. And so we refer to this as the homoclinic structure or the NLS, and it's remarkable, in my opinion, that you can actually describe a so complex phenomenon in terms of very simple ODE. Of course, this is not the only thing you can do, but for the moment, this tells us that modulation instability is a symmetry breaking phenomenon. There is an underlying homoclinic structure. If you want to be precise, it's heteroclinic, but I'm not going into the details. And the periodic orbits are Fermi-Pasta-Ulam-Tsingou recurrence, but this recurrence has non-trivial symmetry. So you can have motion inside one of the I or the 8, and this is a motion in a single well, or otherwise in a double well. Okay, the modulation instability has a very long story. It went back actually in '77 to some experiments by Lake and Ewan, essentially. It was worked in theory by many people, and the field actually reborn in the frame of rogue wave. Okay, I don't have to show this to this community, but just to tell that actually I have a is an infinite dimensional phenomenon. So you can think about modes, and the modes are the Fourier modes. So you can generate many Fourier modes, and I'm going to show this with movies. And so essentially is a representation of the Fermi-Pasta-Ulam-Tsingou. So recurrence is kind of expected, but what is surprising to me is that the recurrence is not trivial, because there is this homoclinic structure. Approaches we can do, as I shown, Fourier mode truncation, so get Hamiltonian ODEs, and I think this is very important, because the homoclinic structure is not a property only of the nonlinear Schrodinger. There are many other nonlinear NLS-based systems which are non-integrable, and you want to describe. I'm not doing this today, but actually we use this approach also in the non-integrable case. But not only that, I mean, there are other pros. The pros I remember to emphasize are that the system highlight the importance of the field phase evolution, which is usually neglected, and gives a suitable, as I shown, phase plane where to project all the NLS evolutions. Of course, NLS has an integrability machinery, so finite gap based approach can be developed, and what one can do is what I call a brute force approach. So once you have data from some experiment, you can do spectral analysis, but this usually doesn't give you much physical insight usually. And so we privilege actually other approaches, which are reduction to simple predictive formulas. Usually you can do this by asymptotic, and one beautiful example is the paper by Grinevich and Santini that I will comment on. Also using exact solution that you can derive or not from finite gaps. So essentially in this talk I will use accommodative doubly periodic solution. Okay, back to the physics. So we want to describe actually this FPUT system. And so we have the ODE and the phase plane associated to that. But now so the phase planes comes from the truncation to 3 frequencies, actually, the pump, the background, and the 2 first order sidebands. And if I start from the orange or blue dot, essentially I got very different behavior. So essentially here I get FPUT recurrence without any shifting. So you can see that the maximum are aligned here. And whereas if I start on the blue, then I get phase shifting from recurrence to the next, from one recurrence to the next. So this is actually not surprising because of the phase plane. So it's simply saying that the NLS gives something which is pretty stiff to the ODE that I've shown. And of course, the separatrix is the, as I said, the Archimedes breeder, well known in this community. So I don't have to spend more about that. So let's show actually two movies. So the first movie is relative to the orange curve that I've shown before. So essentially, I start from the blue. This is the initial value. So it's amplitude modulation. And you follow actually the evolution. So this is in time, and this is in Fourier space. And of course, you can see that there is a compression and a very strong growth of the peak of the field. And this is associated to the broadening of the spectrum. So the maximum broadening of the spectrum is obtained, of course, when the compression is maximum. And if you project the evolution into the phase plane that I've shown, you get this single well orbit. And I want you to note that something that could be interesting for the following is that actually the motion slows down close to the saddle point, and it accelerates where the compression occurs, which is the opposite point. This is important. Okay, again, this is the P-color representation, and this is equivalent to the libration of a pendulum. If I start instead with a frequency modulation, and you can see the blue now, you barely see the modulation because it's frequency, not amplitude modulation. You can see that the orbit that you follow is a double well. And from one compression to the other, you get a phase shift of pi between the sidebands and essentially the pump. But if you get a look at the spectrum is essentially identical to the previous case. So if you measure only the spectrum, you cannot recognize in which orbit you are. And in this case, you are in orbit, which I call shifted orbit, and this is equivalent to a rotation in the pendulum, in an equivalent pendulum. But I want to emphasize one thing, and now in the NLS system, the rotation is less energetic than the libration. So if you wish, is an inverted pendulum, and this is very important if you add some damping in the system. Okay, so when we started this business of measuring this homoclinic structure, that was the state of the art, essentially an experiment made in 2001 in optics, where they have seen, looking at the Fourier spectrum, the growth and then the return to the background, essentially to the pump. But that was only one recurrence, and it was only a measurement made in power. So actually, from this type of measurement, you cannot recognize that there are in fact two different orbits. So actually, this tells us that if you want to go beyond the first recurrence, first of all, you have to be able to measure the phase. And this is, in optics, is not a trivial business. And the other experiment which is relevant was an experiment made by the waterway people, Olivier Quimon and others. And so essentially, even if they pretend to see, they are supposed to observe unshifted orbit, they always get into shifted orbits. And this, now we understand, is due to the losses. So actually, if you want to have a true NLS dynamics, then you have to compensate for the loss. And in optics, you can do this. Okay, so I will go very briefly through this. I mean, this is the experiment that was designed, the credit goes to Arnaud Mousseau. It's actually to measure the pump and the sidebands in nonlinear modulation instability in power and phase. Okay, so what you do is you start with a laser, you modulate, and you inject in a 8 kilometers fiber. And instead of looking at the output, you look at the backscattering. The backscattering gives you information of how the field evolves along all the fiber. And since you want to extract essentially the information about the three principal modes, the pump and the sidebeds, then you need another laser at a different frequency. You modulate at the same modulation frequency, and then at the output on the backscattering, you do what is called heterodynamics in optics. So you beat the output of your fiber at each, essentially at each distance along the fiber, so you can reconstruct completely the evolution along the fiber with this new frequency, and you can extract phase and square modulus, which is power in optics. Okay, there are some technicality that I'm not going to address because the community, I think, is not much interested in that. Another main point is that you can compensate for the loss, and you can do that by using a Raman pump. So a counter-propagating signal that compensates the damping, the natural damping in the fiber. So this was the result that we published in Nature Photonics 2018, a few years ago. And actually, this is the amplitude modulation case. So what I show here is the pump and the sidebands here along the fiber, reconstructed from the experiment that I've shown, and also the relative phase between the two against the fiber length again. And so you can see that in this case, the phase is limited between in the right half plane of the complex plane. So it's between pi over 2 and minus pi over 2. And if you project the evolution into the phase space, you get this orbit that you expect, as I've shown before. And the agreement with the integration of the NLS is not bad. Then you switch to input frequency modulation. So now the relative phase at the beginning, instead of being 0, is pi over 2. And you can see that, in fact, the evolution in terms of power, sidebands and pump is similar, but the phase is completely different because now it's free running. This means that you are actually on these double loop orbits, which are outside the separatrix. Okay, we improved these results in 2020, essentially using an ultra-low loss fibers. This permits actually to use a much longer fiber, 18 kilometers instead of 8, or the starting 8. And again, what I show here is a comparison between the input amplitude. Actually, the top one is the frequency modulation case. So the green is experimental orbit that you trace, and the dashed is from NLS. And again, here is modulus and phase. So essentially, the phase here is free running. And instead, when you go to the amplitude modulation, the orbit is confined into the single well on the right up semi-plane, and the phase is no longer free running. So far so good. I want to emphasize that actually this is not the only experiment which allowed to detect the homoclinic structure of the nonlinear Schrodinger equation in the MI. There were other two, the one made by the group in Rome by Pierangeli, Conti del Re, and with the collaboration of Gunevich and Santini. That was very determinant in terms of theory. I will go back to that. And this experiment is special. Instead of using a fiber, you use a modulation with a bulk crystal and free beams. And essentially, we get very similar results. So I'm not going to comment any longer on that. And an experiment which is also very interesting is an experiment made at the former Alcatel, I think, Huawei labs. And actually, they used a finite gap approach to describe the experiment. So essentially, now they reverse the point of view. They started from a solution in terms of finite gap, And this is a spectral representation. You can see that is a phase shifted solution, like the double loop orbit that I've shown. And the experiment is completely different because now they are looking into transoceanic distance. They were able, instead of using few kilometers, up to 8,000 kilometers. But this is simply because they are using a recirculating loop. And the recirculating loop means that you have to amplify at each round trip inside the recirculating loop. Still, the evolution in terms of that they reconstruct in terms of theta function is in pretty good agreement with the experiment if you average over many observations. And the nonlinear spectrum, this is interesting, should be supposed to be, this is the upper semiplane, so it should be free points, which are the end point of the bands, as far as I can see. But what they got in the experiment is the blue stuff, and so it's very noisy, and it's very noisy because of the amplifier. So this is what I call brute force approach. They start from the finite gap, but at the end of the day, if you want to compare with the real spectrum, you have to do average and filtering of the data, and still the agreement is not that good, which is not surprising because you are propagating over very, very long distances. Okay, back to the state of the art in our approach. And what I consider state of the art is an approach actually developed by Petr Grinevich and Paolo Santini. We discussed that back in 2018. So essentially, you want to have a very simple formulas predicting the occurrence of the first growth peak, ROG event if you want, but I don't like this term because it's not a ROG, it's a deterministic solution. There is nothing statistics here. And also you want to predict the second peak, and for example, in this type of solution. And they came up with very simple formula that I'm going to explain now very briefly. Okay, there were a simple formula before in optics, but in optics this formula is wrong, and the reason it's wrong is the following. Okay, to develop this formula, they actually used a finite gap before, but I'm going to talk about this a much simpler approach, which is developed in physics, let us say. So essentially, you start with the background plus sidebands, and the only approximation you do is very, very small sidebands of the order epsilon. Why? Because you want to have in the complex plane only essentially one band. So this is a restriction, the only restriction. Then you can say, okay, in the modulation instability, I have two things. One is growing. This is a growing eigenvector, and I call it A alpha plus. But there is also a decaying eigenvector, which I call alpha minus. And so you have to project your input and this C1 and C minus 1 are complex numbers. So you project your input into these two quantities. And so one is growing, the other is decaying. And usually people completely neglect the decaying stuff. And now you look at the formula. So the formula is a logarithmic, and the logarithmic is natural because the Archimedean breeder has exponential growth. So the inverse is a logarithmic. But here depends only on the modulus of alpha, the first occurrence, and this is okay. And then when they showed this formula was really puzzled, because then it means that the recurrence, the distance between two peaks depends also on the decaying stuff, alpha minus. So at the denominator of the logarithmic, you have the absolute of the product. And so I was puzzled. So I went myself, okay, forget about this, to do the calculation. Of course, the calculation was right. We trust Petr and Paolo Santini, but just to understand what happens, you can do asymptotic matching. And so you start with sidebands, which are the order epsilon, and they are growing. Then you can match to using asymptotic match, you can match to a breeder and determine the parameter of the breeder. And this gives you the first formula, the one with alpha plus. But now what happens, there is also something which is decaying, and this decays to the order epsilon square here, the alpha minus. So what happens at the second peak is actually this alpha minus, which is growing again, not alpha plus. And the idea by Paolo Santini was actually, okay, so the first one is Z1, the first formula I've shown. The idea by Paolo was actually to exploit inversion in evolution variable Z, and instead match the alpha minus at negative time. And the distance between the peak here and the peak here gives the recurrence distance, the periodicity. Actually could be half of the periodicity in the phase shifted orbits. But this explains why the period of recurrence depends also on the decaying component, which is not straightforward at all. Okay, so once we understood that, we went back to our experiment and tried to actually make a check of this formula against the experiment. So essentially what we did is to measure the distance of the first and second recurrence in terms versus actually the input relative phase. So just to show that the relative phase is very important, is dramatically important, I would say. And in fact, starting from left to right, you can see that actually in this yellow region, you're outside the separatrix, so the orbit is a double loop here. And as you move toward the right, the distance of the recurrence decreases accordingly to the formula, while the second is increasing. And there is a minimum. This minimum is precisely at the critical phase, which corresponds to unstable manifold of the separatrix that I've shown. So you have a very transparent interpretation, because here is the fastest growth actually that gives you the minimum distance. And then if you proceed toward the right, then you can see that you cross the separatrix and you have single loop orbits here, still in very good agreement. And if you keep on going to the right, then the distance grow again, and there is another critical value of the phase, which is a stable manifold of the separatrix, and it's very interesting to know that in this case the pump is not decreasing, is growing at the beginning. So you measure something, you inject sidebands, that these sidebands are giving that power to the pump. So if you want, is an inverted modulation instability. But then once you go back to the background, you start with the usual modulation instability and you follow the loop. So essentially this was to show that our experiment was in very good agreement with the formulas, except we couldn't go at that time beyond 8 kilometers, so we couldn't check where this distances becomes very, very large. We also checked the formulas against the unbalanced case. So if you have asymmetric sidebands instead of symmetric case, you can see that the formulas tells you again where the two recurrences are and also the temporal shift that you expect. And we measured again the power imbalance, these distances, and the agreement is quite good. One thing you can ask yourself, we asked ourselves at that time, is how many, since our apparatus is based on measuring three frequencies, is if you want to reconstruct the full field, how many modes are needed for a good time reconstruction. And so the answer is that three Fourier modes are not enough, but if you can generalize your apparatus to measure 5. And if you measure 5 waves, then you can reconstruct the full evolution. Here is the experimental one compared to the numeric. So it's a pretty good comparison. And you can, of course, measure not only the square modulus, but also the phase. And the phase, again, experiment and and theory is in pretty good agreement. So we measured actually a pi phase jump also that you can have across the peak in the transverse direction and also in the longitudinal direction, but I'm not showing this in the slides. Okay, so thanks to change a bit the approach. This is a more recent one. Okay, we know that there are actually doubly periodic in Z and T exact and NLS solution, and so we asked ourselves if we can use that to fit the experiment. Okay, so these are due to Akhmediev essentially, and were not derived by finite gap. Essentially, it calls first order because you assume that the real and imaginary part of psi are related linearly. And this is a pretty strong assumption, but is verified. And so you can construct full explicit solution, which I don't report explicitly, but still you have the formulas. And so if you ask what is the relation between theta function, of course, there are methods that you can exploit to generate this formula more generally. So in general, what you get from finite gap is quasi-periodic, but here the solutions are strictly periodic in Z and strictly periodic in T, which with period 2 pi over omega. So these are free parameters family, and the free parameters fix the peak of the growth, essentially the peak of the wave. I mean, if I'm looking into the solution, they are of two kinds. So one is called B-type, which is unshifted. I prefer to call it unshifted and shifted because they recall my ODEs, essentially my phase plane that I recalled at the beginning of the talk. So B-type and A-type are actually unshifted and shifted. That depends on three parameters, which are real, and in one case, and two of them are complex conjugate in the other case. Okay, so what I report here is the Fourier spectrum of these two solutions. And it's important to notice that actually the Fourier spectrum is such that at the minimum here, you have a very broad spectrum in one case, but for the A-type, actually all the odd harmonics are zero, exactly zero. So essentially you are left with three waves here and then the higher order, which is very, very small because it is log scale. The phase projection is the same of what I've shown so far. So essentially one is single loop, the other one is double loop. So essentially they're good candidates. So the problem is how can you measure, can you say that actually they describe your experiment, my experiment actually. And well, okay, if we want to say that actually the experiment is described by this solution, you have to have very weak sidebands, minus 20 dB with respect to the pump. That means one order of magnitude smaller than what we used before. This means that we need a longer fiber. And then one can ask, okay, which solution of the three parameter family is fitting our experiment? And so we use a fit by saying, okay, we can choose the three parameters by comparing the Fourier spectrum at the minimum expansion in the experiment and in the theory. And so we end up with, this is an example. So this is a plane, usually where you have one parameter, which is nearly one, alpha 3. And so you have other two parameters. And in these two parameters, what I report here is the frequency. I mean, the color means the frequency of the modulation. And so once you have chosen the frequency, you are along one curve in this plane. And this plane has noteworthy limit. So one is peregrine soliton, which is this vertex. The RB, which is a comedic breeder, is, for example, this line. The continuous wave, the background is this point. The soliton is this point, and the constants of my is this line. So apart from that, and sorry, the denoidal is the x-axis. So once you are here, you can, with this procedure, you select one value of the parameter, and then you have a post-check on the experiment, because then you can measure the z period and see if this fits with the essentially with the solution. And so again, these are two experiments we did. So the first one is single loop orbits, again, starting with amplitude modulation or unshifted orbit. And the other one is with the double loop orbit. And in both cases, the agreement is pretty good. So here the dashed is the theoretical extraction from the solution. So we can claim safely that we observe this doubly periodic solution in the homoclinic structure of the NLS. But what is more interesting is this, in my opinion. I mean, we were actually, I'll tell you the story. I mean, we were working with Matteo Conforti on these solutions a few years ago, and we realized that actually the shifted orbits, the A-type, are not existing only in the unstable region of the modulation, in the modulation unstable region, so it means between 0 and 2 in terms of frequency, but also at higher frequency. And this was actually pretty surprising at that time, but actually is not. So to reconstruct the whole story, Matteo redid all the calculation. So we published again in 2020 FISREV-A, where all the solutions are recalculated. And actually, what I want to emphasize is this, that the solutions which are shifted, the unbroken or A-type one, they exist also outside the band of modulation instability. And this is not surprising, because if you go into the linear limit, which means omega going to infinity, you can easily extract a solution, and this solution is phase shifted. So essentially, this phase shifted solution covers the whole frequency from infinity back into the modulation instability region up to 0. So essentially, the other way to say this is that they survive the symmetry breaking, which is the modulation instability. But the B-type, the unshifted orbit, they are not. They exist only from 0 to 2 in terms of frequency. So I would say that they are genuinely nonlinear. So they occur because of the symmetry breaking. Okay. So next question was, okay, but since we have these solutions which are existing, so the A-type, I mean the shifted type, that exists also outside the modulation instability band, can we measure some amplification? I mean, if we are working with omega larger than 2 and in the stable region, can we measure some amplification? Now, if you go back to the linear stability analysis, of course, the answer is not. But if you define the gain at the maximum, the peak of the sidebands divided the minimum of the sidebands along the evolution, so here is the minimum and here is the maximum, then you realize that actually if you are inside the modulation instability region, then you have a very high gain, and this gain in the solution by Akhmediev is ruled essentially by the imaginary part of the two complex conjugate variable. So the smaller is this imaginary part, the higher is the gain. But if you go outside, they simply collapse to a finite value. So essentially, you still have an amplification, which is quite few dBs, but still non-zero. So the linear stability analysis failed to predict that I can get some amplification, even if it's small. And we actually, Nail was pushing to call this extraordinary MI because it's not the conventional one. And very recently, we made, both in Lille, an optics experiment and in Sydney tank, a water wave experiment to confirm this amplification. So this is now published in PNAS this year. And so you can clearly see that if you have omega much larger than the cutoff, here is 40 giga, the cutoff is at 29, you can still measure these phase shifted orbits and you can still get some amplification. And the same in water. And this is amazing in my opinion, because it's, well, now we are not only I mean, we do experiment as a group in water and optics, but there are many groups that do the same. But this is remarkable to highlight the fact that the two experiments different in terms of, I would say, 10 order of magnitude in terms of frequency, because we are using 40 giga in terms of modulation of frequency in optics and 0.4 in terms of modulation of frequency in water. Okay, so let's go to the second example that I want to emphasize, and is this essentially the effect. What is the effect of losses? Okay, so essentially you add losses to your NLS, and even though alpha in normalized units is much less than 1, the impact is dramatic. And how can you realize this? Okay, again, I look at the sideband fraction as a function of z, but instead of doing a simple plot against z, which is the vertical axis here, I plot this against the attenuation. Okay, and so what I see is the following. Okay, the FPUT recurrence is along the vertical axis again, and essentially what I'm looking at versus alpha is the fact that there are critical value of the losses, where you can see a very sudden increase in length of the occurrence of not the first, but the second, the third, the fourth FPUT occurrence. And you can explain this because essentially this critical alpha corresponds to the alpha at which you can have a separatrix-crossing from unshifted to shifted orbit exactly after you do one turn alpha C1, two turn alpha C2, three turn alpha C4, and four turn alpha C4, and so on and so forth. So essentially you can see that the signature of the separatrix-crossing is a very rapid, very abrupt increase in terms of alpha of the recurrence. And for example, if I take the alpha C4 example, if I project my nonlinear Schrodinger equation into the phase plane, the picture I see is this. So I start from here, I do 4 loops, and then I suddenly jump on the outside orbits. And this jump is very, very slow. I mean, it goes from green to orange. That means nearly 10 units in terms of nonlinear Schrodinger equation. And this is the reason you see this increase in the length. And this occurs only if you start with the unshifted orbit, because you can cross from unshifted to shifted, but not vice versa. So if I start on shifted orbit, the same plot is smooth. Okay, very rapidly, we actually developed a model. The model is again based on 3 waves. So essentially now we have a parameter which is the frequency, which is increases over the dynamics. And the reason is because the power is decreasing exponentially. So the normalized frequency is increasing exponentially. And you write down also an equation for the Hamiltonian. The Hamiltonian decreases. And you can actually simply integrate this equation and have an integral relation that allows you to detect this critical alpha. Of course, this is based on the 3 waves, so there are some, to be honest, there are some discrepancy with the value that we find in the nonlinear Schrodinger equation. Nevertheless, we made an experiment, because in optics you can control the effective damping, because remember we have a Raman pump to compensate the losses. So acting on the Raman pump, we can have actually linearly decreasing losses versus the Raman pump. And so we were able actually to measure and see the first two critical alpha. So essentially, again, this is the same plot we used in theory. So vertical is distance and horizontal is value of effective losses. And you can see the first recurrence is here. Then you can see a second recurrence, but the second recurrence goes increases in terms of distance at a precise value of critical alpha. And then there is another critical alpha here. And the second plot is about the phase, but I'm not going to comment. So essentially, you divide the region into 3 different regions. And in the first one, you cross, you have already crossed after one turn when you approach the saddle point. In the second region, the central one, you switch to the shifted orbit after 2 turns in the unshifted one. And in the third one, you don't have any crossings. So essentially, you orbit into the unshifted orbit always. Of course, in this region, if you would have a longer fiber, then you would see another critical value of alpha, but we are not able to see that. Okay, so this is a third example we published also this year in collaboration with a group of Kasparian and Amin Chapchoub. So essentially, the idea is the following. I mean, suppose you have an Archimedean breeder launched at the beginning. So you are evolving along the separatrix, the blue curve here. And suppose you arrive at a certain point, the maximum growth of the Archimedean breeder here, this point, and you abruptly inflate the phase space. So you essentially switch from the blue separatrix to the red one, and the elliptic point, which is in between here, switches here. Ideally, it would be to switch to have it switched exactly on this point. If you can do that, then you can say that you can freeze the breeder exactly on an elliptic point. So we call this phase space manipulation. And so essentially, if you want to, what we explored is the transition from an Archimedean breeder to a dinoidal solution. I mean, again, from a separatrix dynamically to an elliptic point, which is contained inside the separatrix. And in order to do that, you can show that you need a jump into the ratio between the dispersion and nonlinearity. So I call this ratio 0 and infinite before and after the jump, essentially. And we came up with a very, very trivial formula for the optimal matching. So essentially, the normalized frequency at infinity has to satisfy this formula with the omega naught, the frequency before the jump. And since the frequencies, the two frequencies are in fact the normalization of the physical frequency of modulation, and this has to remain constant for the jump, then you have a recipe in which you can relate the relation between the dispersion and the nonlinearity before and after the jump. Of course, the matching is not perfect. I'm not claiming this. The matching is not perfect. There is no way you can do a perfect matching in the full Fourier space because the Fourier space of the two objects is different, but nevertheless, with this criterion, the matching is pretty good, and we verified this in a water wave experiment. I will go very briefly again. What we are looking at is an Archimedean breeder focusing exactly here where we can have or not have a jump, essentially in the depth. So when the step is absent, when the jump is absent, you get into the focusing. The black is the pump and the yellow is the sidebands. And these are also higher order sidebands, but look at the main modes. So you get the maximum focusing here, and after that you go back to the, essentially to the background, to the initial condition. If you add the step, then you can sort of inhibit this behavior, and the jump stabilize the breather nearly at its maximum. Why I say nearly? Because if you do longer simulation, here the tank is long, only 30 meters. If you do simulation on up to 50 meters, in this case, you can see that there are oscillations. And these oscillations are, of course, due to the fact that the matching is not perfect. I mean, you can never perfectly match again between an Archimedean breather and a dinoidal wave, but still you can freeze. Okay, I see that I'm running out of time, so perhaps I want to go very, very briefly through this. Let me explain this. Okay, this is actually, so far we considered only periodic perturbation, but what about localized perturbation? Okay, two scenarios have been outlined, and one is recently by Gino and co-workers, where actually can localize the input. Actually, there was a former paper by Gennady also. Essentially, a localized perturbation, which in Fourier space is at zero frequency, can develop what we call an auto-modulation. So a Witten region, if you want, which is confined in a characteristic wedge. But there is another scenario where that was actually due to Zakharov and Gelash, Andrei. So essentially, there was again here, also here, a paper by Tajiri and Watanabe, well known, where they say that actually you can form a pair of superregular breathers, and this could be a scenario for the evolution of the nonlinear modulation instability in the case of localized perturbation, which are not at zero frequency. So at some frequency inside the gain, for example, near the maximum. Okay, this the first scenario was actually confirmed by Pierre and co-workers in Lille. So we fully trust that. The second scenario was also confirmed by an experiment by Kibler in optics and Amin again in water waves. But actually, in this experiment, they put in at the beginning a perturbation which is so-called ad hoc. I mean, is a perturbation that arises from the superposition, from the interference of these two breathers. So it's not surprising that we observe the breather, that they observe the breather in some sense. And this is very well known to this community. So it's a complex plane representation. So what I want to very, very briefly emphasize is that in fact there is a coexistence scenario. So in general, what you excite is both the breathers here and the auto-modulation inside the wedge. And this is what we initially did with Gino, essentially to take a more general perturbation. So for example, an envelope of the such type modulating again a pair of sidebands, and actually do IST of this initial condition to show that there is two eigenvalues that corresponds to the breathers, but there is also something which is not discrete spectrum, and that gives rise to the auto-modulation, and the two coexist. I want to do one step further. We did actually with Matteo one step further, and taking the same type of initial condition, generalized actually the approach by Grinevich and Santini to work out a very simple formula where you can actually say where the breather appears in space and time. So essentially, we generalized the approach by Petra and Paolo, but now we included an envelope in the initial condition, and this envelope gives the same formula that I've shown before, is weighting alpha plus, which is the growing eigenvector of the modulation instability. And so once you give me the perturbation, I can calculate alpha plus as a function of t, and tells you exactly where the breathers appear. And the breathers appear at a minimum distance, which I call zeta minimum, and asymptotically they have some asymptotic velocity, which is plus or minus Vs. And this Vs, from this formula, you can easily work out, is amazing simply formula, is a gain of the modulation instability times the width of the envelope. And if I don't have time, but if I go back to the very briefly, perhaps, to the previous slide, you can calculate the velocity rigorously through the IST, and you get this number. But if you do the perturbation, like that formula tells, it's very, very near. So it's a very powerful approach, in my opinion. This formula, you can learn a lot, because you can learn the fact that the breather's appearance needs the envelope to decay exponentially, so such is okay. Also, the exponential minus absolute time divided by t naught is okay. But for example, if you take a Gaussian, even if it's very close to a setch on the peak, the tails are decaying differently, and in that case, you don't get any breather. Still, the formula is valid. You can predict the locus of fast growth. I will show an example. Again, I commented this, the velocity is asymptotically given by this formula, which is very simple. And I don't have time to go through the details, but this is some zoology. So look at for example, at the bottom plots. So you can do the breathers from an asymmetric envelope, and still the formula is working pretty well to detect the breathers. You can have a very slowly decaying envelope, like a Lorentzian. In this case, you don't get any breathers. You get this peculiar form, but still the formula predicts the peak of the occurrence. And you can have also very complicated case where the breather are inside the wedge, and they can interact nonlinearly with the wedge, and this is an open problem. All this is interesting, in my opinion, because this is what's next in the experiment. These regimes is not observed, and we can look for experiments to detect this type of scenario. And this brings me to the summary. So essentially, I've shown that the homoclinic structure, the nonlinear regime of DMI, becomes experimentally accessible. We can use different theoretical approaches from simple to more complex, but still you get the same answer. There are other developments, and I've shown the case of damping, the case of what we call extraordinary mean in the stable region, the case of the phase space manipulation. And also, unfortunately, very briefly, the fact that the localized perturbation can have a very rich behavior, which need further work from the experimentalists and also from the theoretician, in my opinion. And with that, I can stop, and thank you for the attention, essentially.
Thank you very much, Stefano, for the very insightful and interesting talk. Any questions? So there were some comments in the chat. One from Constance Schobert. It's quite long with several important references, I believe. And well, if Connie is around, she could maybe unmute her mic and comment. If not, well, I mean, there are several references, and you can read, well, you all can read them in the comments. And there is a comment from Peter. The dependence on attenuation looks like the multi-bounce resonance phenomenon for colliding breathers in phi-4 models and other similar problems. Again, it's a comment.
At the moment, sorry, but I don't see the chat, so I rely on you to read. And okay, with Connie, we can discuss, because I heard their talk and it was very, very nice. I know many of the reference, I guess, so we can discuss. We can discuss because it's a complicated problem. The second question was the lossy case.
Yeah, so the attenuation looks like the multi-bounce resonance phenomenon for colliding breathers in phi-4 models.
You mean this case? The lossy case, this case?
Peter, if you are around.
This is the one I was talking about. Very interesting picture and very nice talk, by the way, Stefano.
Thank you. Yeah, so what's the point? I'm missing the point.
I was just pointing out that the picture and also the mechanism that you described reminded me of this kind of capture versus bounce phenomenon for colliding breathers in phi-4 models. So, you know, depending on the relative velocities of the breathers, all kinds of interesting things can happen. And you might think that the dependence would be very smooth with respect to incident velocity, but there are these kind of peaks that come about because of some resonances with the colliding breathers at isolated values of velocity. So I'm just remarking about that.
Okay, thank you. It's a good insight to get a look at.
Oh, sorry, but my impression is what we did with Paolo, we simply considered evolution of this only one spectrum point. And the agreement was very good. The influence of small damping or small amplification. I don't know. I think the mechanism may be simpler. You can explain what if you are very close to the bow, if you're very close to the highest point, very small perturbation, if you have very small damping, you have exactly perturbation with the opposite sign, roughly speaking. In contrast, if you have damping and you have HYDW, you have perturbation with the same phase. Maybe it's very naive, but I don't, there is such very simple. I don't think very complicated mechanism should be involved.
Well, I mean, I agree. I guess your picture is based on more on the finite gap, which I would like to learn. But my picture, I think it's quite simple. I mean, it's separatrix-crossing, and I can explain why this separatrix-crossing occurs exactly at some critical value. So that's I don't even need perturbation theory, because I can explain why it occurs exactly at those critical values. The remarkable thing is that at the beginning we thought there was only one critical value, but instead it's not, because you can cross after many turns. So there is an infinite succession of critical values, essentially. But okay, I mean, your suggestions are worth looking at, of course. Both Peter and Peter.
Stefano, do you think if there is amplification that you would have a scenario in which you can go from the shifted recurrence to the unshifted recurrence instead of losses? Okay, if you put amplification, do you think that it's possible to have the opposite scenario of crossing?
Yeah, sure. Because the Hamiltonian is, I mean, as I said in the beginning, it was only a quick comment. But the NLS works like an inverted pendulum in the sense that the unshifted orbits, which correspond instead to rotation in a pendulum, are less energetic than the shifted. Sorry, the shifted are less energetic than the unshifted. And so essentially, if you add amplification, yes, I expect exactly to reverse this picture.
Also, it's in complete agreement. We did numerics and analytics, and yes, it's in complete agreement also with what we did. Of course, we did only mathematical models. We will go from shifted to unshifted if you have amplification, yes.
Yeah, sure, sure. We agree about that, yes.
Hello, hi.
Yeah, hi.
Hi. Yeah, so this is Connie. So yeah, I just wanted to say that it was very interesting, the work of your groups of Trillo and Grunewicz, and how you've correlated the results for perturbed NLS to the physical experiments, and very nicely matching the parameters and the recurrence time, that sort of thing. I just wanted to comment that we had looked at the long-time dynamics of the modulation instability in the context of deep water waves, and having identified this basic phenomena, we correlated it with the lab tank experiments with the evolutions of the spectrum, the NLS spectrum. And so I wonder if it would be interesting to have also this sort of precise matching of parameters and everything like you have today. I mean, to re-examine that.
Yeah, I know. I think, I know that the papers I think I know the papers that you mentioned in water wave. I remember that actually one of the issue at that time was whether the NLS is a good model or not, which now in fibers we fully trust the NLS. So at least in the regime that we are operating. And so the answer is yes, of course, we can re-examine all the experiments in terms of spectral analysis of that you did years ago.
Yeah, we actually used the higher order NLS as the equation.
Yeah,
and okay.
Yeah, also what you have shown in your talk about the damped NLS is, I think, is useful to get a different point of view in terms of understanding the physics, after all, because we can observe this stuff in the experiments now.
Okay. Thank you very much, Stefano. Any other questions, comments? Okay, so we can then just go to kind of concluding discussion. Thanks again. It's really great stuff.
Sure.